Well, hello again. This is presentation number 3 in a series on the subject of the Collatz conjecture. So previously in the first section we've talked about the introduction to describe the Collatz conjecture and outline the proof that we're presenting here. The second section was about 7 theorems that describe the structure of the tree for the Collatz conjecture. And this is a section that maps the odd integers in P onto the signed integers in the Z domain, and it introduces the spiral structure for the tree for the Collatz conjecture. So what we do is we're going to map the odd integers of P that are residues of 1 and 5. These are odd integers without the excluding the multiples of 3. Those are in P, and we're going to map that to the integers in Z. So how are we going to do this? The integers in P have residues of plus or minus 1 mod 6, where minus 1 is the same as a residue of plus 5 mod 6. If the residue is minus 1, then what we're going to do is we're going to add 1 to n and divide by 6, and that's going to be the integer in Z. And if the modulus is, or the residue is plus 1, then what we're going to do is subtract 1, divide by 6, and negate the integer. So that's going to be a negative integer in Z. The inverse is easy to do. You just take the signed integer in Z, you multiply by 6, you subtract 1, and take the absolute value. So the way these root map are shown for the first few integers on the table on the right there. So the root node 1 in P maps to a different root node 0 in Z. A P value of 5 maps to a Z value of plus 1. A P value of 7 maps to a Z value of minus 1. A P value of 11 maps to plus 2. And a p-value of 13 maps to minus 2. So this leads us to restating the Collatz conjecture in terms of the Z-reversed simplified Collatz conjecture, or the ZRSCC, that every integer in Z descends to a root node at Z equals 0. If the ZRSCC is true, then every integer in P in the reverse simplified Collatz conjecture will then correspondingly descend to a root node at n equal 1. And if that is true, then the simplified Collatz conjecture is true, so is the standard Collatz conjecture. We'll talk about the tree in the next slide that shows the integers in the Z domain. And I'll take this opportunity to point out that many of these features of the spiral have been introduced in Fabian Reed's videos on YouTube. You can look them up on the subject of the Collatz conjecture. So this is a representation of the Z reverse simplified Collatz conjecture with the nodes labeled with the integers in Z as opposed to integers in N. So the root is Z equals 0 on the left. It ascends to nodes 1, negative 14, and 57. Node 1 then ascends to nodes negative 142, negative 2, and plus 9. Negative 2 ascends to nodes plus 3 and negative 46. Plus 3 ascends to nodes 2 and negative 30. 2 ascends to nodes negative 1 and 5, and so forth. So if we start at negative 5, that descends to 2, that descends to 3, then to negative 2, then to plus 1, and ultimately to the root node 0. As before, we ascend by going to the right and getting farther away from the root, or we descend by going to the left and getting closer to the root. There are some properties of the tree from the P domain that are inherited in the Z domain. So the first property is from theorem 1 that there's only one descendant for each node in the tree. This is true in Z as well as it is in P. Corollary 1.1 is there aren't any loops in the tree. This is also true in the Z domain, there aren't any loops in that tree. Property number 2 is from theorem 2. There's only one root in at n equal 1. This is true in the Z domain, but the root is at Z equals 0. There's only one root there. We had descent functions in P that was represented by equation P dot 2. There's an equivalent descent function in Z, but it's somewhat more complex. It's represented parametrically as assigned plus or minus 3 times Z plus some constant C divided by 2 to the D for some exponent D. So parameters B, C, and D depend on the value of Z. We'll get to that in a second. The C constant is related to the Jacobs-Stahl numbers. That's OEIS series A001045. That's shown there in the first few values here, 0, 1, 1, 3, 5, 11, and so forth. The divisor 2 to the D is dependent on the D least significant bits of integer Z. We'll see how that works too. So here's the first dozen or so descent functions for positive Z. There's different descent functions for negative Z values. We'll get to that in the next slide. So the way this works is it's a sieve that you sift through starting from the first and going down. So if the Z value has residue 0 mod 2, which is to say it's a positive even number, then the descent function is 3Z over 2. If the modulus is, or the residue is 3 modulo 4, then the descent function is negative 3Z plus 1 over 4. In other words, the result is a negative Z value. If the residue is 5 modulo 8, then the descent function would be 3Z plus 1 over 8. If the residue is 1 mod 16, then the descent function is negative 3Z plus 3 over 16, and so forth. This works all the way down there. So you see each subsequent descent function catches half of the residues of the previous descent function, so that ultimately, if you had all of the descent functions, you would capture every positive Z value. This is the same table, but this is for negative Z values. In this case, if the negative Z value residue is 1 modulo 2, in other words, if it's a negative odd number, then the descent function is negative 3Z plus 1 over 2. If the residue is 0 mod 4, in other words, it's a multiple of negative 4, then the descent function is 3Z over 4. If the residue is 2 mod 8, then the descent function is negative 3Z plus 2 over 8, and so forth. So here we see these descent functions for the negative Z values equivalent to or similar to the descent functions for positive Z. The constant term in the functions is the Jacobs-Stahl series of numbers. For the positive functions, it's 0, 1, 1, 3, 5, and so forth. For the negative descent functions, it starts with 1, and then 0, then 2, 2, 6, 10, and so forth. It's twice the Jacobs-Stahl numbers. The coefficients, linear coefficients, alternate plus or minus 3 for each descent function. And then there's some other relations that are relevant to the derivation of subsequent descent functions. Here's the derivation of the descent functions. We don't necessarily need to go through that in detail here, because the most exciting thing is how this leads us to the spiral representation of the tree. So this is a linear representation of the tree. So we arrange the values of Z starting with 1, then there's a space, and then 2, and then minus 1, then 3, then a space, then 4, and minus 2, and 5, and then a space, and then 6, and minus 3, and 7, and a space, and so forth. So you can see the pattern of the arrangement for the z values, and the spaces are branches back to previous z values. So the first branch is to 0, the second branch there is to node 1, the third branch is also to 0, and then the fourth branch there goes back to node 2, and so forth. We'll see how this makes sense in the spiral representation in the next slide. The root node is 0. The way that the descent is calculated here is by counting along the blue line there. So, for example, if we start with node 5, which is there in the middle, it's a positive number, so we count 5 nodes to the right. So that would land us on the branch back to 2 on the far right. So we would go back to 2 on the line, and that's a positive 2, so that we would count 2 nodes to the right. So that would land us on node 3. 3 is a positive number, so we would count 3 nodes to the right, which would land us on negative 2. Negative 2 is a negative number, so we would count 2 nodes to the left, which would land on the branch that goes back to 1. So that would land us back on 1 at the very beginning. 1 is a positive number, so we would count 1 node to the right, which would land us on a branch that goes to 0. So we would land on the root node 0. So that's how the nodes work on this representation. If we arrange the nodes in a spiral as shown here, then the structure becomes very clear, because every node lands on this spiral in the way that we've shown here, so that positive values are in alternating, go in alternate nodes in the positive or counterclockwise direction, and negative values go in between the positive values, and they go every fourth node, and then the other fourth nodes are branching nodes that go down to a branch on an inner cycle. It's a spiral, so the blue line there is the spiral cycle, and the branches are spokes that radiate out from the numbered nodes that are the base value for the spokes. So, for example, the very first node 1 has a spoke that goes out through all the other cycles above it, and then node 0 has a spoke that propagates off to the right, and so forth. So if we have a number that's positive, we count in the counterclockwise direction, and a number that is negative, we count in the in the clockwise direction. So, for example, if we start with node 11, which is in the left-hand side in the intermediate cycle, we would count 11 clicks to the right, which would land on node negative 8, which is near the bottom there. That's a negative number, so we would count 8 clicks to the in the clockwise direction around the other direction. So that would land us on negative 6, which is also a negative number. So that counts 6 more nodes in the clockwise direction, and that lands us on the red spoke that descends down to negative 1. So we're at negative 1, and that's a negative number, so that we would count 1 click to the clockwise direction. That would land us on 2, which is positive. So now we count 2 clicks counterclockwise, which lands us on node 3, which is also positive. So we count 3 clicks counterclockwise, and that would land us on negative 2, which is now negative. So we count 2 clicks in the opposite direction, which lands us on the spoke that descends down to node 1. And then node 1 is positive, so we count 1 click to the counterclockwise direction, which lands us on node 0, which is the root node there. So that's how the spiral works. Again, the main points of the spiral here is that there's a blue line representing the spiral cycle, And so in general, we count along the cycle until we reach a spoke. And if we have a spoke, then we fall through to an inner cycle of either one or two or more inner cycles. And then the red spokes, the dotted line spokes, are the transition between cycles. You can see the spokes all tend to descend down to the inner cycles that eventually land on the root node at 0. And this is the main point of the spiral. So this kind of summarizes the spiral properties. So we've talked about positive and negative values based on alternating nodes. Every cycle in the spiral has 4 times as many nodes as the next cycle inside. The starting cycle with root node 0 has 8 cycles, and then the next, 8 nodes in the cycle, and then the next cycle after that has 32 nodes, and then the next cycle after that has 128 nodes, and so forth. We also speak of semi-cycles, which are half cycles, and each semi-cycle has twice as many nodes as the previous semi-cycle. The spoke branches, shown as red dotted lines in the illustration, branch to lower cycles in the spiral after every 4th node, and every 4th red spoke falls through more than 1 cycle, and every 16th red spoke falls more than 2 red cycles, and so forth. So the descent to inner cycles becomes progressively steeper, although less frequent as you go along. Only 2/3 of the nodes can be reached by counting along a spiral cycle, while 1/3 cannot. That's going to be a theorem that we come up to soon here. So we'll talk about that. One example here is the red spoke between values of 5 and 6 on the cycle. That cannot be reached along the cycle. But between that same spoke between values of 21 and 22 can be reached from z equal -14. So the descent here from value of -14 will be directly to the root node at 0. That covers our introduction to the Z spiral and the Z map, and we'll have more